Good morning and welcome to our continued discussion on analyzing functions and graphing. While I set up everything, let me know in the chat whether you can see and hear me. All right, then we'll just wait for this program to start up and go. Now we have every time I'm going to review the graphing steps, where we are in that discussion, what still needs to happen, and so on. Because it's good to have a big picture. Well, I prefer to know where I am in the grand scheme of things. We have our warm-up where I just identify the function if I can and find the y-intercept. It's always nice to make some progress. Then we had our second step, asymptotic behavior, where I look at long-term behavior. Are there asymptotes? Maybe I care to know what happens close to the asymptotes. Maybe I just have some arrows to be refined later. Either way, I want to identify asymptotes, identify long-term behavior, see in that sense what this function is doing. In no way can I get a good picture of the graph at this stage, but it is an important step that I have to do. Next, we want to know where is the function increasing and where is the function decreasing. So I'll call that increasing, decreasing behavior. And then we have a couple more steps to go, but one thing at a time, right? Okay, so increasing, decreasing behavior. If I have a function, let's call it f of x, we officially say it is increasing on an interval. Let's call the interval x1, x2. It can really be anything. Let's call it a and b. Let's call it a and b actually. That's going to be better. A to b. If I take two x values in this interval and I compare the y values, the function values, let's have a picture. Saying and writing different things makes it confusing. For any two x values in this interval, let's just see what happens. I don't care what happens outside of the interval. Let's suppose I have an A and I have a B interval. This is my window. Nothing outside matters. If I compare any two x values and the y values, the points need to be going up in terms of the y value. So the second one needs to be bigger than the first one, or the first needs to be smaller than the second. I need to be going up in some way. It could be wobbly, but from A to B, I need to be going up. One of these endpoints, one of the x values could be the very end point. I still need to go up towards it, so increasing. So it's not a super complicated concept. Just picture the graph. I have to go uphill. I have to go up, increasing. And then I can do the same thing for decreasing. Just for the sake of being complete, I write out the definition, but that's never something that I'm going to ask you to state formally. It's good to see how the language looks. Function f is going to be decreasing on some interval a to b if I compare the function values between any 2 points, x1 and x2, in this interval. Could be the endpoints, could be interior points, doesn't matter. I need to be going downhill in one way or another. Could be slow. You see up here, it's slowly going down, then it speeds up a little bit. Either way, it's going downhill. So if I compare 2 points, any 2 points in this window, in this interval, the first one needs to be greater than the second. Now again, look at this, don't look at it, just understand what we mean by increasing and decreasing, downhill, uphill. There could be many different versions of going uphill, right? Of having a function be increasing. For example, I could go really slowly and then increase and get steeper and then maybe slow down again. Lots of things can happen. Regardless, in this window, what do the tangent lines look like? I have a little flat guy here. He's not perfectly flat. He is still going up. And then he's getting steeper, 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 then maybe slowing down a little bit, heading towards flat in this example. But for all these tangent lines, all the tangent lines have positive slope values. Might be small, might be big, but they all have positive slope. So what does that mean? Well, what is the slope of a tangent line officially called? Slope of a tangent line. Does anyone remember what is our fancy word for slope of a tangent line? It's the derivative. And I have a name for the function, so I'll just write my f prime notation. Positive, positive. Now, there is a little technicality that I just want to get out of the way because so many books, they just don't do it right. Or they glance over it, they don't address it, and it, to me, has become sort of the elephant in the room. We need to talk about these things. So let's do something like this, where I have a point where it's perfectly flat, for example. And then it picks back up. This graph is still increasing throughout. Because if I compare any 2 points, it could be this flat one, it is going up. If I compare anything on either side, it is going up. Everywhere, comparing 2 points, they're still going up. So technically, this has to be a greater than or equal. Technically. With the exception that I have a perfectly horizontal line throughout, well, then I wouldn't even bother with this increase and decreasing question anyway. So I like an equal sign as an option there to cover this possibility, which does happen. If you think about, for example, the basic polynomial x cubed, it has this property. Let's look at y equals x cubed. I know what the graph looks like, or I should. It is perfectly flat in the center. Yet from left to right, compare any 2 points. Any 2 points. I'm always going up. It's increasing for all x values. Yet there is a flat spot. And then it picks back up. And that's okay. It doesn't change the increasing nature. So technically here we have equal signs. And there is a distinction between increasing and strictly increasing, where strictly increasing doesn't allow for this. We're not interested in that. We're going to have an equal sign. But the nice thing is, It's the derivative. The derivative being greater than or equal to 0, and I'm increasing. So it's a very simple check to make. I just need positive or not negative slopes. Here it's going to be the same. Decreasing, I'm just going to have I'm going to be okay and allow the equal sign for reasons I just said. Even though it's sometimes going to be flat, my slope lines, they're always going to be negative. So all slope values in a section like this will be, all slope values are negative or 0, meaning that my derivative needs to be less than or equal to 0. So again, for increasing decreasing behavior, this means that I just need to check where is the derivative. I'll just relax and say always positive, negative, understanding that 0 is okay. Where is the derivative positive? Where is the derivative negative? And then I'm going to have the answer to where it goes uphill, where it goes downhill. So it's actually quite simple. Did I do it on this page? Right. When we looked at asymptotic behavior, I looked at the function. When I look at increasing, decreasing behavior, I'm going to now look at the derivative. So let's do some examples and see what there is to see. Well, I have this guy. Might as well finish this guy. The derivative, oops, there's no need for a little denotation, is going to be 3x squared. And you see this is always going to be greater than or equal to 0 because take any negative x value, the square is going to make it positive. In the case where x is 0, then I have a 0 slope, but I satisfy the requirement of being at least 0, so I'm increasing everywhere. But of course, this function isn't very interesting, right? It's a basic function. I already know everything about this guy. We want to go through our types of functions, at least most of them, to see how do I handle this in more complicated situations. So let's start with the easiest one, which is a polynomial. Now, you can very easily get situations where the polynomial doesn't factor very nicely. So I just want my specific example to have a good first example. This is zoomed out. I have it on my other screen, but it's so zoomed out I can't even see it. Okay, there we go. X cubed plus 3x squared minus 9x plus 4. All right. I don't know what that looks like. I have an idea of something based on x cubed. It has a couple of turning points maybe. It's not too wild, but I don't know exactly. Okay. So we would have maybe in a larger graphing question, we would have already done asymptotic behavior. We would have seen that the graph goes up far to the right, down far to the left. We have a y-intercept of 4, but we don't have much. Increasing, decreasing behavior will really start to fill in the shape of the graph. But for that, I need to find the derivative. So I have 3x squared, all basic properties, plus 6x minus 9. Now I want to factor this. And I can start by taking out a 3. That's going to help me a whole bunch. And we're not going to make the factoring super complicated. We've done in pre-calculus, you've done a ton of these things. There's no need to test you on the most difficult factoring, because that means I have to remember all those things as well, and you very rarely use them. But here I kind of need to. So hopefully this will work. It's going to be a plus 3 and a minus 1. Okay. So now I'm going to use the table that I introduced last time here again. So what I'm going to do maybe first, just do it on the side here, is identify where this derivative is 0. Well, because I have it factored, it's actually something I could just read off. It's when any of the brackets equals 0, which is going to be when x equals -3 or 1. So in this factored form, super easy to find where the derivative is 0. Those are going to be the numbers that I'm going to mark off on my number line. Then on the left, I'm going to list every factor that I see in my derivative. Whether they're crucial or not, get into the habit of listing everything. Now these numbers, -3 and 1, split up my x values into 3 separate intervals. 3 is always going to be positive. So it doesn't really do much, but it is contributing something. I don't want to leave it out. Sometimes it really matters. X plus 3 is going to be 0 when x is -3. We've done this before, and I've asked you to be comfortable with why it's going from negative to positive. X minus 1 in isolation is 0 when x is 1. It's also going to go negative to positive. Please double check. Don't look at this and say, oh, they're always negative to positive. No, you have to look and be sure. If this looks a little different, it could very much be different. Okay, so let's remember this is the derivative. This table is now set up to say where the derivative is positive or negative, because that's exactly what I need to be able to say something about increasing, decreasing behavior. So the table looks the same, but now it's applied to the derivative, not the original function. So when x is -3, x plus 3, this bracket is going to be 0, and it's going to make the whole thing 0 because I'm multiplying. When x is 1, the second bracket is 0, making the whole thing 0 because of multiplication. For the first interval, I have a positive and 2 negatives being multiplied together. My answer will always be positive. For the middle interval, I have 2 positives and a negative. My answer will always be negative. For the last interval, positive. I cannot stress how useful this table is. I use it all the time, even still after I've done thousands of these. So there must be something to it. Many books you'll see, they just look at the last row here, and then you just have to hopefully do everything correct in terms of guessing to find the last pluses and minuses. Yes, this last row is the only row I'm really interested in moving forward, but where do they come from? They come from an interaction of the individual factors. And because those factors in isolation are super easy to look at, I can just look at each one quickly, then combine them, and know exactly where the end results come from. So it still has benefit. If I don't write down this middle, then I could very easily make a mistake, and the middle is not hard. So what does this mean? I'm going to leave a little space here. I'm going to write something in a second, but I now want to write a full sentence saying where the function is increasing, where the function is decreasing. Now notice that this sentence refers to the function. Even though I'm looking at the derivative, I am making conclusions, making statements about the function, the original. F is increasing on, first interval is -∞ to -3. Infinity always gets a round bracket. -3 gets a square bracket because there is a point, but nothing past that. Then I'm going to turn downhill. 0 is okay. Downhill, no, that's not increasing anymore. And of course, I also have the last interval, 1 to infinity. Now officially, when you merge these two, it's by a union symbol. But if you have never seen that before and it makes you uncomfortable, I just need you to list all the intervals. Doesn't matter. And then my function is decreasing. There's still some new things happening here. Let me know if you have any questions. Oh, I missed the question, sorry. Just to clarify, -3 line and 1 line are 0 because the derivative of them is 0. Everything in the table now refers to the derivative at the top of the screen there. The original function is out of my mind for a second until I come back to the sentences. So I have zeros on the lines because the derivative function, see here, derivative, is 0. So the table is done for the derivative, even though I'm using that information ultimately to make a statement about the original function. So I'm sort of temporarily looking at different things. And so I can conclude the original function is decreasing on -3 to 1. Include because for both of them, they sort of have an overlap at 0. And 0 is okay for either one of them, sort of where the windows are attached to each other. Yeah, definitely interrupt at any stage. Any questions? There's always something new and something I need to look at in the right way, and people get confused. When do I look at what? I'm not graphing the derivative, yet I'm analyzing it to make a statement about the original function. That's very important. Okay, so if I zoom out and look at this again, my first function should always be a polynomial. It's the simplest one I'm going to have. By finding the derivative, factoring it, and then analyzing that, I prefer the table. It's not a necessity. I'm never going to force you to use the table, but I cannot think of anything that's going to be easier than this table. I still use it all the time. It's so nice. It makes everything as clear as it could possibly be. If I look at the derivative at the bottom of this table here, remembering that the derivative refers to the slopes of tangent lines, right? Positive means my tangent lines are going up. I don't know how exactly. They're going up. I just have a general, just going to have a general upslope. Then 0 is going to be horizontal tangent line at -3, and then I'm going to have a downslope again. And around this x equal to 1, it's going to go downslope, horizontal, upslope. So these slope lines can give me a picture of what's happening to the graph. It's going to make a little crest, and then a little cup, a little dip in the graph, and that's exactly what's happening. Ooh, I guess I can make a new page. I wanted to squeeze it all in here. I guess that's a bad idea. Fine. Again, we don't know exactly what the graph looks like, but the picture is definitely forming. So if I set this up, I would, at this stage, if I wanted to graph, have the information from step 2, which is, oopsie, not that one, 4 for the y-intercept. Maybe 4 sits over there. That's the information I would have coming out of step 2. Now I have some more information. That something interesting is happening at -3. And on the way to -3, which let's put -3 over here, I'm increasing. But there's a point sitting at -3. Where is it? Is it high? Is it low? I don't know. I need to find the y values. I need to find the y values corresponding to these x values. So it's a little tedious, to be fair, but we can quickly do it. It needs to be done, so let's do it. So I want to know what is happening at -3. I can't type in my calculator and speak, so it might seem a little quiet for a second. So I have negative 3 cubed is negative 27 plus 3 times 3 squared is also going to be 27. Oh, that's easy. Then two negatives will be another 27 plus 4. It looks like 31. Correct me if I'm wrong. I'm trying to do this fast because we have a lot of functions to get through. And we are, strangely enough, behind schedule. It's weird. Check the other one. Should get a negative 1. That now tells me where these guys sit. So the first one actually sits super high. I'm just going to put it up here at 31. What's happening there? A little crest. Whoopsie. At least touch it. A little crest is happening there. I'm just drawing it to remind myself. It might not look exactly like that. Then something's happening at 1. Let's put 1 over here. And my point is actually quite low at negative 1. And what's happening there is a little cup. So you should see how the shape is starting to show now. I'm going to go up, turn, go down through, not straight, curvy, go down through the y-intercept, and then go up again to infinity. See how that familiar shape that you have seen in pre-calculus, that N shape, is starting to form. And the increasing decreasing behavior is a big step forward into filling in the graph and adding pieces to the puzzle. Okay. Now for a simple polynomial like that, you can probably have a pretty accurate graph at this stage, but in some other cases it's still not going to be perfect. But that is a discussion for later. Exactly what's missing, why there's a step 4, and so on. Okay, so that was a polynomial. Let's see a rational function. And I don't want to make this function overly complicated. Actually, something that you could do transformations on and figure it out that way. We are now having more sophisticated tools to not rely on transformations because not everything can be done with transformations of basic functions in an easy way. That's the good thing is that this isn't a difficult function, that I could sort of guess what this is. The downside is that if I have to find the derivative, this is going to be a quotient rule, unfortunately, which in application isn't terrible. The bottom squared, derivative of the top times the bottom minus the top times the derivative of the bottom. I picked easy polynomials, so this derivative isn't terrible. Let me just, actually, I don't want to do it there. New line. Then I have here, these ones don't actually matter, right? I want to show them when I find the derivative to show that I've used the quotient rule completely, but in simplification, they don't actually matter. I have an x here, I have a minus x, so there are no x's. I have a 1 and a plus 1, so it's a 2 over x plus 1 squared. And now I have a reason to simplify this, because moving to my table, I need to see which pieces are actually being multiplied or divided here. Regardless, I have the derivative equaling 0 when? When is this derivative going to equal 0? For which x values? That is my question to you. Which x values will make that derivative 0? This is where you say something. Anything at all. This is your moment. Negative 1? Plug in negative 1 into the derivative. What do you get? Put it into your calculator. Let's do it. 2 divided by negative 1 plus 1 bracket squared. Bad times, bad times. Undefined. because when I plug in -1, I'm dividing by 0. So yes, there is another one here. Whoopsie. There is another one that I need to take note of, and that is where the derivative is undefined. That is going to be when x equals -1, when the denominator equals 0. To make this answer, the derivative y value 0, I need the numerator to be 0. And in this case, that is not going to happen. Numerator equals 0. Not going to happen. But I need to look, right? So I have two of them now. I have to check where is the derivative 0. Okay, in this case, the numerator doesn't have an x in it, so never. But there are still interesting x values. And those are the ones that make the derivative undefined. So the polynomial didn't give me the full picture. There's more here that I have to check. Where is it 0? Where is it undefined? But of course, in the case of a polynomial, it's never going to be undefined. In the case of the rational function, it could be. Regardless, out of these two checks, and it's only going to be these two, 0, undefined, I am going to list all the x values that come out of that. And in this case, maybe a little boring, it's only one of them, only the -1. Regardless, a simple table is just better. I'm listing everything, the 2, and there are 2 x plus 1s. And my interval is only split up into my x values are only split up into 2 intervals. There was only one x value that came out of this. They're going to combine to give me the derivative. Now 2 doesn't do much, but it is there. I don't want to miss it. It's always positive. X plus 1 is 0. When x is -1, it's going to go negative to positive. And because I get these simple pieces, x plus or minus a number, it looks like it's always negative to positive, but definitely check. Be sure. This second x plus 1 is exactly the same. Yes, I could have grouped them, but then I deal with something squared, which I need to slow down and think about. Having simplest possible pieces, even if they double up, just makes it easier. So now I have a different situation. At x equal to -1, the derivative is undefined, not 0. To the left, I have a positive and 2 negatives. My answer will always be positive. To the right, I have all positives. So if I look at the slope lines, it's going to go positive, something is going to happen, and then positive again. It's not quite clear at this stage until you bring in what happens from step 2. But before we do that, let's just write down our sentences. My function is increasing on. Now I can't say everywhere. That is not right. Why? Because when I look at my function, which is what the statement is saying something about, this guy is undefined at x equal to -1. So I can't ever include -1 in any statement like this, because there is no point to compare. So I need to make sure that -1 is excluded from this set of x values. So -infinity to -1, round bracket. There is no point that I can have at -1. And also, I'm going to use the union symbol because I have to be proper, but you don't have to. -1 to infinity. So it's everything except -1. Now, when we see more examples, the little things that you have to keep in mind will become more clear. But I'll just emphasize again, it has got nothing to do with the table. It has got everything to do with the function. The fact that the derivative is undefined is irrelevant. It's the function that is undefined at -1. That is why I'm excluding it. So you have to always remember that the statements ultimately that I'm trying to make are in reference to the original function. Always glance back. Have a look. What is my original function? Does this statement make sense? Because often the derivative doesn't know what you're trying to do. It's just saying, here I am. This is my property. Do with that what you will. I have to think about, well, what am I doing with that? Look back at the function. That is what I'm saying something about. Now, if you want to graph it, you would have done step 2 first. You would have done asymptotic behavior first. And we would have seen there's a horizontal asymptote of 1. There is a vertical asymptote at -1. So you would have already had some graph information. Let's fill in what it would have looked like after step 2. We would have found our vertical asymptote. We would say, well, it's one of those two. It's one of those two. Don't really know, don't really care. Step 2 is only some of the puzzle pieces. We would have had a horizontal asymptote. It approaches it in some way. It approaches it in some way. I don't know. Don't really care either. And we had a y-intercept, right? Y-intercept, when I plug in a 0, I get -1. So that would come from step 1. I'm just going to put it a little bit higher than usual. Forget the scale. Okay, so this is what we have after step 2. And of course, you've practiced. We've done a lot of these. This should be quite straightforward, especially for a simple function like this. No real work was required. Now, we have some extra information that the derivative gives me, that it's undefined at -1. Well, of course, there is no graph at -1. There's no point. How can there be a slope of a tangent line when there is no tangent line? There is no line to be tangent because there's no graph, because there's a vertical asymptote. So what I find from the derivative agrees with what I have so far. Now it says I'm increasing everywhere else. Everywhere there's a graph, I'm going up. I'm going uphill. Now look at this. If I take this bottom arrow as my choice, I'm going to go downhill. And that is not happening. So the only way for me to go uphill always is to come to the horizontal asymptote on the left from above. I'm going to go uphill to the top arrow of the first two. Then I need to go uphill towards the y-intercept. I can't have this top arrow anymore. It has to come from the bottom through -1. I can't be doing this because then I would have a downhill section, and that never happens. So I have to come at the horizontal asymptote on the right from below. And this is why I said last time that once we get to step 3, choosing which arrows are correct is quite straightforward. It's all because of the increasing and decreasing behavior. There is only one arrow in each case that could possibly work. I don't have to make that choice early and figure out which arrow is correct, because when I come to increasing, decreasing behavior, it's going to follow right away. Now all I have to do is make a graph that is reasonably pretty. Because this one is so simple, there's not much missing here. And I can just fill it in. I have to make sure I hit this y-intercept very well without being too wobbly. Oh, what happened there? Nothing happened. There we go. All of the pieces work together to form the picture, to form the graph. And in this simple case, that was pretty much all I needed. All right. How do we feel about that so far? There's a lot of things to do. We can't skip a lot of examples. We need examples to see all there is to see. And if it takes us a little longer, it takes us a little longer. These things, we're getting ahead of ourselves, actually, right? These things are not in the midterm. We stopped the midterm at exponential and logarithmic functions. So everything we do here is still getting us ahead. But if you look at the actual schedule, we're a little bit behind. That's okay. We'll catch up. Don't worry about it. I'm not going to update the schedule when this is still the same topic. We'll just finish when we finish. So we want some examples that show us all the interesting things there are to see. And that mainly comes in when we have fraction powers of x, our last type of function. Now, to keep it as simple as possible, for the first time you see this, I'm going to look at just one term, and I'm going to look at x to the 1/3. Now, I can write it as x to the 1/3 or cube root of x, of course, and you should see that this is defined everywhere. It's defined for all x. It's not the square root. Cube root's defined everywhere. Cube root of anything you can find. So I don't have any asymptotes. No asymptotes or anything. So out of step 2, really nothing is coming. Not much. Okay, so let us see, what does the derivative tell me? Well, for the derivative, I'm not going to use the root version. I'm going to use this version because I can then directly apply the power rule. So it's going to be 1/3 x to the negative 2/3. Now I don't want to look at this version. I liked it for the power rule and for nothing else. So I want to maybe leave the third in front, then move it so I don't see a negative power of x. And perhaps you like the root version moving forward. Always know that it's an option, like so. And I do like the root version for anything other than derivatives. And I'm done with the derivative now. I had a reason to clean this up because I need to now see, where is this function equal to 0? Where is this function, the derivative, undefined? So there's no benefit right now to make the fraction power of x function complicated. Let's just look, this is in that type. Let's just look at a simple one that we can quickly do. Where is this derivative equal to 0? Is the question for you. Have you learned from the previous example? Or every example is teaching me something, actually a bunch of things. Where is this derivative function equal to 0? For which x values? Silence is not an x value, last time I checked. But maybe you mean none. You're saying nothing? It's none. You're right. Never. Again, not 0. But it's good that you're saying this, so that you can learn. If we don't say something, even if it's wrong, we're not going to learn. It doesn't stick. By making mistakes, you remember it way better. It's way better. When the only things that can make this fraction 0 is numerator being 0. A denominator equaling 0 will make it undefined. It is important, but it wasn't in the first one, it's in the second one. When x equals 0, the denominator will equal 0, and it will make the whole thing undefined. So, of course, you said that on purpose, just so someone can say something. But please, please understand that when I'm looking at a fraction, which one, the numerator or denominator, which one affects which result. Very important. And it happens all the time. All the time. Don't feel it's just you in any way. That's why I'm making a point of this. That people swap the roles of the numerator and denominator. I can have a denominator, it doesn't matter. The answer will never be 0 until the numerator equals 0. Okay, so out of this, not much is coming, but I have one interesting point. X equal to 0. So I'll just mark that off. So my x values are split in 2. Okay, I have a third floating around, and I won't write the 1, of course, that's doing nothing. My cube root of x squared. So the pieces that I have to work with in the case of fraction powers of x look a little different, often. Not always, often. The third is always going to be positive. This is where I really like the cube root, the root version, which in this case is a cube root. It's going to be 0 when x is 0. Of course, this all combines to make the derivative. Because this piece features in the denominator, it makes the whole thing undefined, in this case the derivative. Which side do I want to do first? Maybe the left side of the interval. I need to fill in pluses and minuses. To the left of 0 for x, I have negative x values. But when I plug it in there, I work inside out. I square, making it positive. Cube root of a positive number is positive. For positive x values, of course, it's going to be positive. So you see here, it's not always going to go negative to positive. Sometimes it's the same, sometimes it's flipped. You need to think about the piece that you are working with. And I see here, 2 positives will make a positive, 2 positives will make a positive. So it looks like nothing is happening. I have an upslope, bad times, upslope. Okay, this example, we don't need the fraction powers of x to be complicated to show us its complications, I'll call it. So now my sentence. Again, my sentence refers to the original, and this time it's called y, is increasing on what? Do I say this? Sorry, that was an ugly infinity, I apologize. Or do I say this? It's one of them. Which one is it? We have 2 minutes. But don't take 2 minutes to respond. This is our last little bit for today. And then we'll do another example and another one and move on and just take as long as we need to take. We can't skip these things. They're too important. Because I can't trust that you're going to discover all of these little things, and when you encounter that in a problem you're doing on your own, are you going to know what it all means? No, that's my job. That's why I'm here. I agree it's one of them. This is the first or the second. And this is where I need to train myself to remember all conclusions I am making is in regards to the original function. And you see here, even though the derivative is undefined at 0, which clearly it is, the original function is defined everywhere. What is the cube root of 0? It's 0. The original function has no problems. It has no asymptotes, it has no holes, it has nothing. It's perfect. It's actually the y-intercept is at x equal to 0. Let's get a picture of the graph that we would have at the end of step 2. We would have a y-intercept right there at 0. We would know it's going up, we would know it's going down. That's all we know. There's a point. It's all good. And this is a good example to show that Just because the derivative is unhappy with an x value doesn't mean the function is unhappy. Function is perfectly happy. Now, this is a first example where I haven't seen something like this before. What on earth is then happening? I have a graph throughout, one piece. Nothing strange is happening. Yet the derivative is undefined. If I think about straight lines, almost all straight lines have a slope. Almost all straight lines fit y equals mx plus b, except one. Except one straight line does not have a slope. Its slope is undefined. It's the vertical straight line. So if there is a graph here, there's a tangent line, yet there is no slope. The only way that can happen is if I have a vertical tangent line, which is what's happening here. And very often with fraction powers of x, I have a vertical tangent line that needed to curve away a little bit. So this I have not seen before. If I have a function that's defined everywhere, yet the derivative doesn't exist, vertical tangent line. Vertical tangent. And I get these interesting things when I look at the fraction powers of x type of function. But I mean, that's okay. I need to see it in an example, maybe a couple, to get more comfortable with it. The first one's never going to be super comfortable. That's okay. That's okay. It's still always increasing. Compare any 2 points. Compare the y value. Always going up. It's always going up. It's just super steep. As steep as you can imagine for a moment. And then it flattens a little bit again. All increasing. Now, of course, we need more examples. I have a couple more to do, but we have to pause it here and then pick it up again tomorrow. And it takes as long as it takes. But I'm happy that people are answering questions. Try, say something. Only when you sort of hear yourself, how do I think about this? What would I say is the answer? Right or wrong doesn't matter. We are learning, and that's the only thing that's important. You're now going to remember this way better than someone that didn't say something, that didn't show up to a live session. It's way better. Don't ever worry about saying the wrong thing. Just say something. It helps you. All right. We're pausing here until tomorrow. Think about it. Bring questions if you have them. We need to be able to be comfortable with all of these things that I am mentioning by way of our examples. All right. All right, good morning, everybody, to our continuing discussion on graphing and increasing, decreasing behavior of functions. Before we get going, can I just get confirmation in the chat that you can see and hear me? All right, let's do this. Now, last time, let's think where we were. We are looking at increasing and decreasing behavior. And for that, we analyze the derivative of the function. And we ended with, oopsie. Hey, get out of there. We ended with y equals x to the 1/3, a simple version of a fraction power of x type function. And we saw that this graph has a vertical tangent line at y equals 0. So let's just make this a little bit more complicated. It's not as if these functions will always have a vertical tangent line, but often that's what we see and want to be prepared for when I see this type of function. So as I see these more and more, when I do my warm-up, I identify the function as a fraction power of x. I should think, ooh, watch out for vertical tangent lines. It's not a guarantee, but I should be aware that it is a possibility. And I'm building that experience slowly by looking at more and more examples. Let's make it a little bit more interesting, not super interesting, a little bit. And we will see these functions again. Let's look at this guy. X minus 1 all to the power of 2/3. Let me just make it clear what my denominator is. It is a 3. All right. So now I have no idea what this graph looks like. I see a fraction power. Yeah, the fact that it's x minus 1 in the bracket just means there's a little shift happening. It's not really a different type of function. So I am going to find the derivative. And that's going to be a chain rule. It's something to the power of 2/3. So the first part of the chain rule will be 2/3 times the something to the power 1 less, which will be negative 1/3, times, says the chain rule, by the derivative of that inside something, which is 1. Now for the purposes of moving forward into my table and seeing what is happening with this derivative, I do want to clean this up as much as I can. For me, personal preference is to get rid of the negative exponent. So I will move it to the bottom. And perhaps I want to just remind myself that whenever I need to see it this way, this is just the cube root. Maybe that helps me, but either one of these I like before I move forward. So I have a reason to simplify because it's going to make my life easier for my upcoming table. So I'll do it over here. There are two things that I want to check. I want to check when is the derivative equal to 0 and when is the derivative undefined. Always going to be those two things, no more, no less. And the more we see them, the easier they will get. So I see that in my numerator, I only have 2/3. There are no x's, and only the numerator can make the function 0. So that's going to be a never. I do see I have something in my denominator. When x is equal to 1, I will get a 0, making the whole thing undefined. All right. So we will list all the numbers we get out of these two checks. In this case, there's only one. And I'm going to list all the pieces that I see. I see a 2/3 and I see a cube root of x minus 1. Together, they combine by way of multiplication and division to give me my derivative function. Now 2/3 is always positive. Not a problem there. But I don't want to miss anything here. If that 2/3 was a negative 2/3, then it plays a bigger role. So I just get into the habit of listing absolutely everything I see in my function. Cube root of x minus 1 is 0 when x is 1. And because it's in the denominator, we've said it makes the derivative undefined. Okay. Now, this looks perhaps a little bit uncomfortable. To the left of 1, is this positive or negative? A shortcut that you can take to make it easier is I can take a representative number inside this interval. It's 0, so it's inside this interval. Plug in that number, but then I get cube root of negative 1, which is negative, and it's going to be negative for all of them, as long as I've listed everything that I got from these checks. And I've split up my table correctly, you can take a representative number, and whatever it does for that piece, the whole section will do the same. So I'll put a representative number of 2, something easy I can easily work with in my head. 2 minus 1 is 1, cube root of 1, positive. So that's one thing you can do if the component that you're looking at is a little bit less familiar. Now, a positive and a negative will always make a negative. 2 positives will always make a positive. So my slope lines are going down, bad things happening, going up. So it's not a little cup that it's making in the conventional sense, because I do not have, I'll emphasize it here, there's no horizontal tangent line here. That would be when the derivative is 0, and that's not the case here. So I do go from downhill to uphill, but let's see what's happening here. Let me set up a graph so I can at least visualize something. So, of course, we're just doing step 3. And again, that is not sufficient to clearly know what the graph looks like. If I did step 1 and 2, I would see that it goes up on either side. There is a y-intercept. Whoopsie. What's my y-intercept here? It's going to be 1, right? I don't know where these lines are coming from. Y-intercept of 1. Let's put it over there. And obviously something is happening at 1. Something unpleasant is happening at 1. The derivative is undefined. Yet, because I can see this as the cube root of x minus 1 squared, cube root is defined everywhere, this function is defined for all x values. So the function has no problem with any x values. It's the derivative that has a problem. And when I have a situation like that, for our level of functions, that's when I get the vertical tangent line, that there is a tangent line at 1. The only way the derivative cannot exist at the same time is if it's a vertical tangent line. Now I'm coming down and I'm going up. I'll give you a little, I guess, preview. You are not expected to know what this looks like at this stage, because we don't have all the steps, we're just doing one step. I make a sharp point there, vertical tangent line, vertical tangent line. The more I see this, the better it'll get. I have a function value, it's defined there. The derivative is undefined, has to be a vertical tangent line. Okay, but looking at this function, if I did step 1, identifying it as the fraction power of x type, I know from the start to watch out for vertical tangent lines. And when I have all the steps, all the pieces will hint at that shape. So the more I do it, the better it's going to get. Slow and steady. All right. Again, feel free to interrupt me if you have any questions, like always. Okay, let's do an example with an exponential component. Those are probably my favorites because when I take the derivative, they're not going to be super difficult. I'm sticking to the natural exponential function. But at the same time, they give me more interesting examples than just polynomial or rational function, while not being too extreme with vertical tangent lines and difficult things like that. So I would do steps 1 and 2 maybe, or maybe a test question could just be find the intervals where it's increasing, decreasing. And I just realized we never wrote down our sentences here. I got a little excited about the graph. I'm sorry. We should write our sentences. Let's at least see the table here. Okay, so I can say here y, whoops, not eraser mode. You should always write your sentences. Y is increasing on 1 to infinity. Do I include 1 or not? Do I put a square bracket or a round bracket? I always want to make these intervals as big as possible. Even though the derivative is not defined, there is a point there. The graph is defined there. Include it. It's not about the derivative. It's about the function itself. And then y is decreasing on negative infinity to 1. Include it. If I compare any 2 points and 1 happens to be one of those 2 points, it's going down. It's part of that interval. So always write these sentences. I just forgot. Okay. All right. So before I move on to this example, actually, I want to classify these points that keep coming up that are interesting. When I look at this first example, I checked where is the derivative 0, where is the derivative undefined. We got an x equal to 1 coming out of that. And what I get here is a point where things are changing. It's going downhill to uphill. There's a turning point. It's an interesting point in the graph. We're going to call that a critical point. It's really critical to the property of the graph, to the features of the graph, to the type of graph that I see. Critical point is going to be 1, 0, the point 1, 0. Or I can say critical point at x equal to 1. Okay. Now, I don't have my other examples with me, but we saw other points coming out of this check, derivative equals 0, derivative undefined, and we'll call them critical points. So let me just classify that. A critical point, I won't be too fancy with this definition, is going to be when my function, my derivative is equal to 0 or my derivative is undefined. Undefined. All right, so those two situations could give me a critical point. And I always check those two. And, capital and, I have to have a point. It's critical. It's important for my table out of these two checks. And it has to be a point. Meaning my function is defined there. There has to be a point there. Now, if you think back to, let me just go quickly find that example that we did, the rational function one. We did this. You can look back on your notes. We did that yesterday. We found the derivative to be 2 over x plus 1. Everything's squared there. So when we then did our derivative equal to 0, we found never. Our derivative undefined. Yes, that was when x was equal to negative 1. This, however, is not a critical point because the function is not defined at x equal to negative 1. The original function has a problem there as well. It was a vertical asymptote, right? quickly graph this. We had a vertical asymptote at -1. Horizontal one doesn't actually matter right now. We had a fundamental problem at -1. It jumps over. There is no point at x equal to -1. So it can't be classified as a critical point. It has to be critical, but it has to be a point for me to call it a critical point. Okay, so let's keep that in mind as we look at this function, and then we will see what the critical points are, if there are any. Okay, so I'm doing step 3. Step 3. Derivative is what I need to find. Clearly the product rule. Derivative of the first times the second plus the first times the derivative of the second. Now I want to clean this up. I want to know, moving forward, what is the best version I can get? Well, I'm going to take an e to the x out, and I'll have an x plus 1 or a 1 plus x left. That's the best I can make it look. I have a positive exponent there, so it stays above the line. Then I want to check, where is the derivative 0? Where is the derivative undefined? Always those two things. No more, no less. So now I have the luxury that I don't have a fraction to worry about. So it's going to be when either one of these two equals 0, right? It's going to be when either e to the x equals 0 or when x plus 1 equals 0. So I have from the second one, I certainly have a -1 for x. When is e to the x equal to 0? Is my question to you. When is e to the x equal to 0? If I have a product, then I have to check each one of those factors, right? And whenever any one of them equals 0, that's an x value that I need to list. And I need to make sure I have all the x values. If I miss one, my table is going to be messed up. Everything is going to be messed up. I need to not miss one. So I get -1 from the second, x plus 1, obviously. But the other one, e to the x equal to 0, is also one that I need to check. But I know what my e to the x graph looks like, and I know it's always above the x-axis. It's never going to touch. There are none. So -1 is the only point. But you need to know. So never is the answer for e to the x equal to 0, and therefore I only have the -1. Picture the graph, read it off. It's all there. And undefined, all of these things are defined. I'm not dividing by 0. It's all good. So that's a never. So the only point of interest in terms of increasing, decreasing behavior is x equal to -1. I'll call this my potential critical point because I've done half of the check. I've done the top part. I need to make sure it's actually defined there. So we can check at this stage, or I'd like to do it after actually, but it doesn't really matter. I've cleaned up my derivative. I have a potential critical point. I'll check the function later when I write my sentences. I've sort of got into the habit of doing everything at the end. I don't know why my line is so long, because only -1 is a point of interest here. So everything I list, e to the x, x plus 1, and they together give me the derivative. It has to be multiplication or division. I could not have taken the top, which had 2 terms. Okay, e to the x, again, I read it off my graph. It's always positive. X plus 1 is 0 when x is -1. It's in multiplication, going to make the derivative 0. X plus 1, check it. It's going to go negative to positive. So I have a positive and a negative. gives me a negative answer. Positive, positive gives me a positive answer. So my slope lines are going to go down, horizontal tangent, up. So a nice little cup shape that I get there. I don't know what my lines were doing there. Oh, there was one cup there. Whee! There we go. All right. Well, let's write our sentences. F is increasing on -1 to infinity. Do I include -1? Yes, I do. Because I have a y value, plug it in. I can get a y value. Now, I don't really care right now what the y value is. The important thing is that I get it. So y value exists. This function is defined for all x, because why not? E to the x is defined everywhere. X, no division by anything. There's no problem at all. I can maybe write without. I just don't want a decimal number here. It's going to be negative e to the -1, right? Whatever -1 over e is. Who cares? It exists. That's the only thing that's important. And f is decreasing on -infinity to -1. Critical point? Yes. It's at x equal to -1 because it came out of my check of the derivative and there's an actual y value. There is a point. Critical point. But of course I have no idea what the graph looks like. Who knows? And I'm going to leave this a mystery because I don't want us to think that we're expected to know. I have no idea what this graph looks like. I need all the pieces of the puzzle. Personally, I still need all the pieces of the puzzle unless I've seen the exact one before. The fact that I've seen maybe x times e to the -x is a completely different function. I can't guess even what this looks like. Does it have asymptotes? I have to do step 2. I don't know, but that's not the point right now. So in the midterm as well, in a test, you might be asked to just do a single step. And you won't know what the graph is. And you're not going to be expected to graph it either. Just make sure that you can write these sentences at the end. Very important. If you don't write the sentence, I cannot give you all the marks. I need to see that interval. I need to see what you're including and everything. Okay. Any questions so far?
Please remember to click the like button if you enjoyed the video and to subscribe if you want to be notified of more videos. Thank you.